Okay, so in this video, there's not really one specific thing I want to look at. I just want to kind of look at some more miscellaneous limits. So I guess just like more limit examples, basically. Just some of the other cases we might see that we didn't explicitly cover in one of the other videos. So mostly I just want to look at, like I said, some examples. So let's look at this one, for example. This one doesn't really fall into one of the other categories. So we have the limit as x approaches 0 of 1 over x plus 5 over x times x minus 5. Okay. Now, first of all, notice both of these, especially obviously with the first one, right? The limit as x approaches 0 of 1 over x. You can go ahead and look at the graph of this, but, we mentioned, sorry, I wrote this wrong. This should be of 1 over x. If we do direct substitution here, we get 1 over 0. And this implies that the limit is not going to exist. Specifically, it's going to be going to infinity or negative infinity. In this case, it's going to infinity from the right side and negative infinity from the left side. So we would say that this, we wouldn't really say it's equal to anything. We would just say it does not exist. We can't even say it's equal to infinity because it's going to infinity from one side and negative infinity from the other side. So it's not even going to the same infinity. So regardless, our addition rule for limits only works if the limit exists. So it doesn't make sense to take the limit of each of these parts individually anyway. So what we want to do is we want to kind of try to simplify this somehow and see if we can come up with a different answer algebraically. And of course, when we have two fractions like this, really the only thing that we can even try to do is to find a common denominator and maybe see if some things cancel out. So that's what we're going to do. So we're going to take, there's already an x in the denominator of this one. So we just need to multiply this part by x minus 5 over x minus 5. And then we'll have a common denominator. Okay. So we have x minus 5 on the top here, plus 5 from this one, over x times x minus 5. Okay. So the 5's cancel. And we have the limit as x approaches 0 of x over x times x minus 5. Okay, now the x's cancel. So we have the limit as x approaches 0 of 1 over x minus 5. So now we can do the direct substitution and we get just negative 1/5. Okay. So even though we didn't get that 0 over 0 form, there was still a way to find the limit of this just by doing some kind of algebraic manipulation. So the 0 over 0 form isn't an end-all be-all for whether or not a limit exists. That's just invisible because of the current form of the function, the current way that it's written. Okay, so if we just rewrite it, essentially, we might be able to find what that limit is, even without the 0 over 0 form. Okay, so now let's look at some other examples here. Okay, so let's look at the limit as x approaches 3 of the square root of x minus 3. Okay. So here, we want to really think about the function here, right? So we might be tempted to just go ahead and do direct substitution, right? And then we're going to get 0, which is a perfectly fine output. But why do we not want to do that? Well, I said that the limit doesn't really care about the domain. What I meant by that was that the limit doesn't care about the domain at this specific value, right? It doesn't care if the function is defined at 3. But if you go back to the definition of a limit, it does specifically say that the function needs to be defined in an open interval around 3, right? So this means that it needs to be defined for some values to the left of 3 or to the right of 3. And it doesn't matter how many, just, it needs to be to its immediate left and its immediate right. And I think this will make sense if we look at it graphically. And actually, I was going to draw the graph, but you can just look at the graphing calculator here. Right, so if we look at the square root of x minus 3 here, right, this function is defined for all x greater than or equal to 3. So remember that a limit is only exists at that point if the left and the right limits at that point are equal, right? So the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right. The limit as x approaches 3 from the right is indeed 0. We can confirm this from the graph. That's the point that it's going to from the right. The limit as x approaches 3 from the left, there is no from the left, right? This function is not defined to the left. So the limit overall is not going to exist because of this. Okay. So specifically, the limit as x approaches 3 from the right of x minus 3 is equal to 3 minus 3 equals 0. And that's fine. But the limit as x approaches 3 from the left of x minus 3 does not exist. Okay. So this is where the domain of a function comes in handy. The domain of this function is 3 to infinity, and the limit specifically says it needs to be defined in an open interval around 3, meaning a little bit to the left, a little bit to the right, but here it's not defined a little bit to the left of 3. Okay, so with that in mind, I think that's a good transition into looking at a piecewise function and how we would find the limit for a piecewise function. Okay, so let's say that we have f of x equals 4x minus 3 if x is less than 2, and x minus 3 squared if x is greater than or equal to 2. Okay, so we want to find the limit as x approaches 2 if it exists. Okay. So in order to do that, 2 is the transition point of this function, right? It's where we are going from this part of the function to this part of the function. So we should check the left and the right hand limits. So first, the limit as x approaches 2 from the left of f of x. Well, as x is coming in from the left, we're on this part of the function, right? So at 2, we're at the bottom part of the function. But if we're to the left of 2, immediately to the left of 2, we're still on this upper part of the function, the 4x minus 3. So when we're approaching the function from the left, this is the part of the function that we're looking at. Okay, so this is going to be, we can just do direct substitution on this part since this is a part where we're at. So this is going to be 8 minus 3 is 5. And now we do the limit as x approaches 2 from the right, okay, of f of x. Now, immediately to the right of the function, we don't really care at all what happens at x equals 2. We just care about immediately to the left and immediately to the right. So immediately to the right, this function is on this part, right? The x minus 3 squared part. So we go ahead and put in 2, and we get -1 on the inside squared, so we're going to get 1. So we see these do not equal each other, of course. So the limit here does not exist. Okay. So again, we only care about immediately to the left of 2, immediately to the right of 2. If I change this to this is, let's say that this is just greater than 2, and then let's say it's equal to like 25 if x equals 2. Okay. Then this doesn't change the limit at all. The limit does, it really has nothing to do with the output at 2, right? A lot of times we see examples where they do happen to be the same, and I mentioned that's when a function is continuous, which we're going to look at separately. But if we're just looking at the limit itself in a vacuum, it has nothing to do with the output at 2, right? So we only care about what is happening immediately to the left of 2 and immediately to the right of 2 to find the left hand and the right hand limits, and then whether or not they're the same thing, which will inform us about whether or not the overall limit exists.